Hey everyone, welcome back to ML for Nerds. This is the fourth video of Generative AI Crash Course. Today we are diving deep into Generative AI architectures. We'll look at the architecture behind different Generative AI models like ChatGPT or Gemini, etc. We will also look into the evolution timeline of the Generative AI. So let's get started. In the last video, we looked at the transformer architecture in detail. This is how the architecture looks like. Basically, it has two blocks. One is an encoder and the second one is decoder. Encoder takes the input sentence and generates the embeddings and passes those embeddings to the decoder. Now decoder takes the previously generated text. That's what this means, shifted right. The previously generated text it takes as input along with the embeddings from the encoder. And it uses both of the information through multiple attention blocks to generate the next word. Okay. Now we got this new architecture. It's a state of the art for the sequence prediction because this model was designed for sequence prediction. Now I want to see how can I use this architecture for different NLP tasks. Sequence prediction is not the only NLP task. There are many more like sentiment analysis or comprehension, etc. Right? For example, I want to use this architecture for sentiment analysis. How can I do that? First of all, can I use the transformer architecture for sentiment analysis? Yes or no? What do you think? Let's understand what do we need for sentiment analysis. For sentiment analysis, the input is text and the output is category. That means it should take a set of sentences or paragraphs and it should analyze the sentiment of the paragraph, whether it is a positive or negative sentiment, right? So the input is text and output is category, just like a classification task. How can I use this transformer architecture for the classification task? We know that the encoder is for generating the embeddings and the decoder is majorly for generating the text output, right? But in case of sentiment analysis, I don't need to generate any text, right? I need to classify the given input text. So what should be the architecture here? I don't need to generate the output text. I just need to give the category for the input text. If I don't need to generate any text, I don't need the decoder, right? I can only use the encoder part for generating some features and then use those features for getting the category, right? So whatever text input is there, I will pass that as input to encoder and encoder will give me some embeddings, right? Some embedding vector. That vector I will give it to some fully connected layer to classify the category. That is enough. I don't need to have this decoder, right? So the architecture for sentiment analysis looks like this. Your input is a set of words or paragraph, and first of all that input text will be converted to embeddings and then position encoding will be added. So finally you have some set of embeddings. They will pass through multiple encoder blocks and the output of encoder will be a set of embeddings again. These embeddings, these are nothing but features, will be passed to a classification head. This is nothing but your FC layer, fully connected layer. And this will finally classify whether the sentiment is positive or negative. That's it. So this is an example for sentiment analysis. So what do you understand by this example? The point I want to make here is we don't need decoder and encoder both in all the use cases. Some use case may need only the encoder blocks. Some use case may need only the decoder blocks and some may need both. This is the example where we need only the encoder blocks from the transformer. We don't need the decoder. There is one more example which uses only the encoder blocks. That is nothing but BERT model. If you read some papers from the NLP, you might have already heard about this BERT model. This is very famous model from the Google Mind for natural language understanding. This model is also based on the transformer architecture and it uses only the encoding part. Okay, so this is the BERT base, that means the same encoder 12 times, and this is BERT large where it uses 24 blocks of the encoder. This model is also a major milestone in generative AI evolution because the concepts used in this model, in the BERT model, is used in the latest Gemini models. Okay, now we have seen the examples where only encoder part is used for the NLP tasks. Any thoughts on the NLP application where we use only decoder? Any guesses? So what is the purpose of decoder? Decoder purpose is to generate the text output. And what are the inputs to the decoder? The inputs are previously generated words and also the input embedding from the encoder, right? So do you think of any application where you need to generate only the text output, right? Do you think of any model which can generate the text which we use in our day-to-day life? ChatGPT, right? ChatGPT generates the text word by word or sentence by sentence, you can say. ChatGPT model or the models which belongs to the same family, which are GPT models, uses decoder-only architecture. So the GPT models uses only decoder block from the transformer for generating the text output. Okay, so this is an example of GPT-3 model where it used the decoder block for generating the text output. Okay, this is the simplest model. Now, can you think of any other application where both encoder and decoder are required? If you remember our previous transformers discussion in the last lecture, we used the example of language translation, where you need to convert a text from one language to another language. That is one example use case where you need both encoder and decoder. So this is an example of language translation where you give the input sentence in one language and you expect the transformer model to generate the output in a different language. So here you need both encoder and decoder. So this is how different models have evolved from the transformer architecture for different NLP tasks. So the transformer architecture, one main advantage is it is very flexible, that different blocks or only the subset of architecture can also be used for solving different NLP tasks. Even the ChatGPT is based on transformer architecture. It uses only the decoder module, right? So far we have seen transformer model used to solve the NLP problems. Now let us go one step further and see how the transformer architecture can be adapted to computer vision domain. That means dealing with images. So the question is, can we use transformer architectures for computer vision tasks? Consider the simplest use case of image classification. In computer vision, image classification is one of the simplest tasks. Can we use the transformer here? Before deciding whether we can use or not, we need to decide how to give the input, because the input is image now. So the transformer usually takes words as the input. Now how can I give a single image as the input to a transformer? So if you take the analogy from NLP, a sentence or a paragraph consists of multiple words and all the words you are passing to a transformer parallelly. Similarly, if I can divide the image into multiple blocks and pass those blocks parallelly to the transformer, will it work? If I divide the image into patches and pass the image patches just like here to the transformer, will it work? So they have tried this idea. This idea led to a new type of architecture called vision transformer. So this is the architecture of vision transformer and this is for image classification. Here the input image is divided into multiple patches here. So if you see this image, it is divided into 4 patches like this, and these patches are given parallelly to the transformer as input. Now earlier in NLP case, the words are converted into embeddings and then position encoding is being used to maintain the relative position of the words. Similarly, in images also, even though we are dividing into patches, we need the position information. So we need to know which patches are coming together. So these images will be converted into the equivalent embeddings, and those embeddings will be added to the position embedding as well to get the final embeddings. And that final embeddings along with the position encoding will be passed to the attention block. So this is the transformer block, or you can say attention block. So this is usually an encoder block, multi-head self-attention and feed-forward network. So there are multiple encoder blocks inside this, and the output from this will be the embeddings for each and every patch. So this patch, the embedding will be this. Similarly for this patch, the embedding will be this, like that. So how many patches you have sent as the input, those many embeddings will be generated from the total transformer block. Now these embeddings will be passed to a fully connected layer or set of fully connected layers, which is a feed forward network that will do the classification. With this architecture, the transformers entered into computer vision domain as well, and the architecture gave comparable results, if not the state of the art, in the image classification task. And there are many variations came on top of this architecture to improve the accuracy further. So this is an example of using transformer architecture for image classification task. This is similar to our sentiment analysis task, right? So in case of NLP, we do sentiment analysis. In case of computer vision, we perform image classification. Now, just like how we generate text based on the user input, can I generate the image based on the user input, right? I want to generate an image just like how we are able to generate the text. How can I do that? The first question is, can I do that or not with the transformer? Yes, we can do that. And this is an example. This is the architecture of DALL-E from OpenAI, and this generates the images from the user prompt, which is nothing but a text. So there is a model called Clip. This is also from OpenAI. Basically, this is used for combining the text as well as the image embeddings into a common embedding space. That means if you somehow combine the text written here and the image here into a common space, then we can generate one from another, right? So first we give input as text. It has the text encoder. It will give some embeddings. And then there is a prior, which is kind of mapping. This mapping is basically converting the text embedding into the image embedding, the equivalent image embedding. So this is a learned representation or learned embedding space where you have the information for an image and the corresponding text, both of them in the embedding space. So if your input is text embedding, it will give the equivalent image embedding, and this image embedding will go as input to the decoder, and the decoder will generate the image output based on this embedding. So this can be similar to your decoder in autoencoders, or this can be as complex as diffusion models. So with this, we can generate the image as well based on the user input. So far we have seen the transformer evolution in the NLP tasks. That means different generative AI models or bigger models came in the NLP domain. At the same time, they entered into the computer vision domain where vision transformers or image generation models have come up. Now, I want to do the combination of these two. That means I want to create a single model which can generate the text or image based on my preference. So a user can ask the model to generate the image or ask some question and answering. So a model should be able to generate both text and image. That means the model should have multimodal capabilities. So what do you mean by multimodal? There are different modes of data. So that's what multimodal means. So these models are called multimodal architectures. So the evolution of generative AI came in that area next. Researchers have developed the generative AI models for text generation and image generation. Now the models have evolved to do both of them with a single architecture. And this is not only for text or image, it can be extended to generating an audio or generating the video as well. Okay, so these are called multimodal architectures. Let us see them. This picture shows the common working or the framework of multimodal architecture. Suppose this is a generative AI model. Multimodal architecture means it can take different types of inputs. That means it can take text, it can take image, audio, video, or any other modalities. And every modality will have its own encoding part to generate the embeddings, and that will be converted to a different modality which depends on the type of output you need. Suppose I gave text as the input and I need image as the output. So I will have a text encoder, and then after that in the decoder part I will have the image decoder. Similarly, if I want text as the input and video as the output, so I will have text encoder, and in the output I will have video decoder. So encoder and decoder depends on the type of modality it is dealing with, either in the input or in the output. Okay, these other modes can be tabular datasets, Excel sheets, or PPT, any other thing. So the examples of such models are GPT-4 from OpenAI and Gemini model from Google. So both of these models accept different types of input. You can actually upload an Excel sheet into GPT-4 or Gemini model and ask it to analyze some data in that. Upload a PPT, you can upload a Word document, you can upload an image and ask some questions about that. So it accepts different types of inputs. At the same time, they can generate different types of output as well. Okay, so this is how generative AI field evolved from the transformer revolution, evolving step by step into different domains and evolving the models with improved capabilities. First, it started with solving only NLP tasks, but at a larger context, larger range. Then it went into computer vision domain as well, and then combining different domains together into a single model, which is multimodal architecture. Now let us look at the timeline of these generative AI models. So we have been discussing that it started with the transformer architecture in 2017. Then in the next year, two important models got released. One is GPT-1 from the OpenAI. So this is the first generative model based on the transformer. So it is used for generating the text based on transformer. And then BERT model, which is from Google Brain. This is very famous model. This is basically for natural language understanding. So more deeper understanding of the natural language. And it also introduced the concept of pre-training. So before this BERT, there was no pre-training or transfer learning in NLP. Transfer learning is very famous in computer vision domain, but there is no transfer learning till the BERT model in NLP. This paper has introduced the pre-training and transfer learning concept for the first time. And this is the major breakthrough in the further generative AI architectures. Because you can pre-train, that means you can train with lot of unlabeled data set which is available. So all you need is having bigger models. That's it. So in the next year, 2019, the next version of GPT came, and also T5 model, text to text transfer transformer. So this is also a major improvement on top of this. This is also from Google. And in the next year, GPT-3 got released, which is very bigger than GPT-2 model. It's like order of magnitudes bigger than GPT-2. And this is one of the breakthrough of generative AI models, having very bigger models using pre-training. And it has showcased very good improvements over the previous models in terms of text generation and context understanding. So researchers have understood that as you scale the model up, it will have more capabilities and it can solve complex problems. And at the same time, in the 2021, OpenAI itself has released a model DALL-E, which is for image generation from the text input. There are many versions came after that, DALL-E 2, DALL-E 3, like that. Even till date, DALL-E 3 is one of the best model for generating images. And then in 2022, GPT 3.5 model got released, which is very famous, which became very successful. And this is the initial base model behind the ChatGPT. So you all use ChatGPT. The basic model which was used earlier was GPT 3.5 behind ChatGPT. Later it was replaced by GPT-4, and now GPT-4o, GPT-4o mini is being used in ChatGPT. But GPT 3.5 is one of the earlier model used. And then later in 2023, multimodal architectures have come up from different companies. GPT-4 is a multimodal from OpenAI. Gemini is a multimodal from Google. Similarly, ImageBind from Meta. Llama is an open source model from Meta. So these are all different models came in 2023. Then the research got an exponential growth. So many models started coming up from different companies all over the world. These are just some highlights from 2024 from big companies. I might miss a lot of things here. I'm keeping only few highlights here. So there are multiple models from Google came. After that, Microsoft has improved their Azure platform and have integrated so many models into that. Copilot got released. Many laptops got released with Copilot as a base functionality, right? So many things happened in 2024. And along with that, agentic AI, this is a new framework on top of the Gen AI. So it started coming into spotlight. And then 2025, it's been only 2 months, but the trend continues and there are a lot of models. And the recent model which came into spotlight is DeepSeek. This is from the China company. And this model has made news that it used only fraction of the cost which is used by OpenAI, and it has reached the capabilities equivalent to the OpenAI models. So using reinforcement learning, of course. So this was a deep dive into the evolution of generative AI models. So I started with the architecture evolution, how different architectures came up from the transformer architecture for solving different tasks. And then we saw the timeline of different models coming from different companies and how the research has evolved. So AI is evolving rapidly. Every alternate day there is a new model coming up, breaking the charts. So what do you think is the next big breakthrough? Let me know in the comments. So that's all from this video. Don't forget to like this video. I have put a lot of efforts for this video, and I have simplified so many concepts to make people understand, as this is a crash course. Thank you. See you in the next video.